So we can also calculate delta H, heat of reaction, from standard enthalpies of formation. So we can measure it experimentally using calorimetry, or we can infer it through Hess's law like the problems we just did, or we can use standard enthalpies of formation. So delta H is the change in enthalpy. And so we can define zero to be something that's convenient, because exactly where zero is doesn't matter as long as we all agree to call this thing zero. So just like we measure changes in altitude relative to sea level, we choose to measure changes in enthalpy relative to the enthalpies of pure elements in their standard states. So the standard state is a set of defined conditions. So if you have a gas, the standard state for a gas is the pure gas at 1 atmosphere of pressure. If you have a liquid or a solid, it's the pure substance in its most stable form at 1 atmosphere of pressure and the temperature of interest, which is usually 25 degrees Celsius. It's 25 unless it's specified otherwise. And if you have a substance that's in solution, it's that substance at a concentration of exactly 1 mole per liter. So this is what we've defined as the standard states. The standard enthalpy change is delta H with this degree sign, or the 0 here. So that degree means standard enthalpy change. That's when all the reactants and products are in their standard states. The standard enthalpy of formation, now we've got this enthalpy, the standard, and the F for formation. This is the enthalpy change when 1 mole of a pure compound is formed from its elements in their standard states. It's also called the standard heat of formation. So the elements must be in their standard states, and that is the case because for pure elements in their standard states, the heat of formation is 0. And so we're going to measure these changes relative to those elements. Got some redundancies in the slides there. So this is table 7.5 from chapter 7 in your textbook, and it shows the standard heats of formation for a number of different elements and compounds. There is a larger, more complete table. I think it's Appendix B in the back of the textbook where they show a lot of stuff. Even that is not a complete one. If you look in the CRC, there's just pages and pages and pages of fine print. So here we've got bromine, and here's Br, and here's Br2 and HBr. For Br2 liquid, the heat of formation is 0. That tells me that's the standard state for bromine. And we can look at the periodic table and come up with that as well, because bromine is one of the diatomic elements, right? So its regular existence is Br2. The periodic table shows Br as blue, which means it's a liquid at room temperature, like water, right? Water's blue. So bromine's a liquid at room temperature. So this is the standard state for bromine, a liquid. And so that's 0. Br, here, this is also bromine, but that's not its standard state. This is individual atoms in the gas state. And so if you have those, the heat of formation for those is 111.9. And the units here are kilojoules per mole of the thing.
It's not diatomic in the gas state.
Well, it would like to be diatomic in the gas state, but you can make it be individual atoms. And so this table doesn't show Br2 in the gas state, but you could look that up. And my guess is that that is only a little bit above 0, whereas this is significantly above 0, which means you have to put a fair amount of energy into it to break those pairs up. Most compounds, like HBr here, have negative heats of formation. That means when HBr forms, it releases energy into the surroundings. Carbon is an interesting one. There's lots of different compounds for carbon, Here we see elemental carbon, so just atomic carbon, solid, but there's two forms here. There's graphite and diamond. There's actually other forms of carbon as well, but they're not on the table. And so how do we know which one is the standard state? It's the one that says 0. So graphite is the standard state, and diamond is close, but not quite. Okay, so let's look at how we could do this. So the standard enthalpy of formation for methane is minus 74.6 kilojoules per mole. And if we go back to that table and find methane, there's methane, minus 74.6. So we write a formation reaction. If we want to calculate the heat of formation for a compound, we have to write a formation reaction. And so these are always going to use the elements in their standard states, and they're always going to give 1 mole of the compound. So we're going to look up the standard states if we need some help, and so you're going to find the form of the element that has the heat of formation of 0. The definition requires that we make 1 mole of product, just because we decided that. And so we'll see some equations here that are going to have fractions, because that's what's needed to make 1 mole of product. So if we want to write the formation reaction for carbon monoxide, we put carbon monoxide as the product, and then we look at the chemical formula and identify what elements are in that compound. Well, there's carbon and oxygen. So here's carbon and oxygen. But those elements have to be in their standard states. So carbon, we look it up and we find that carbon, solid, graphite is the standard state of carbon. O, we could look it up, but we can also deduce it from the periodic table. We find oxygen in the periodic table. Is it a diatomic element? Yeah. So it should be O2. And then is it a gas at room temperature? Yes. So it should be a gas. So O2 gas. Now this isn't balanced, is it? This is 1 carbon and 1 carbon, but over here there's only 1 oxygen, and there's 2 oxygens. And normally what we do is we would put a 2 here and a 2 here and balance it. But we need there to be 1 mole of product, because that's what we have to do. So one approach is to balance it the regular way and then recognize, well, I've got 2 here. I need to divide this by 2. And this is a 1, and I'm going to divide that by 2. And this is divided by 2. And so we end up with carbon plus 1/2 O2 to make 1 CO. So it's a little different than how we balance regular equations. We need to make sure that the product is 1 mole, and there's always 1 product. The reactants are always elements. So to balance this, we're going to use whatever coefficients we need so that we have a coefficient of 1 here. And then we can look up the standard heat of formation in the table. For this one, it's minus 110.5 kilojoules per mole. Heats of formation will either be given as a table for an exam, or the specific ones you need will be provided in the problem. You don't need to memorize them. The only ones you should recognize is an element in its standard state has a heat of formation of 0. Okay, write equations for the formation of sodium chloride and lead nitrate from the elements in their standard states. Include the values of standard heat of formation for each equation. Let's do the first one first. So here we've got sodium chloride as our product, and it's a solid. And what are the two elements present? Sodium and chlorine, right? Well, what do you think the standard state for sodium is? It's a metal, right? And on the periodic table, its symbol is black. That means it's a solid. So Na, solid. What about chlorine? It's a gas, because its symbol is red on that periodic table. And is it diatomic? Yeah, so Cl2. And then we need to balance this. We want 1 mole of sodium chloride. So 1 mole of sodium is great, but 1 mole of chlorine, Cl2, gives us too much. So we need to put a 1/2 here. And it's not that we're using half of a molecule. We're using half a mole of molecules. Okay? It's not half an egg, it's half a dozen eggs, right? You could buy half a dozen eggs. You can't buy 1/2 of an egg, right? They don't like that. So then it says include the values for delta HF. So we go look it up. So here's our table, and my pointer doesn't work now. And so we can double check our elements. So there's sodium and the 0, so that tells us we got that correct standard state. And chlorine's up here, and we chose the correct standard state for that. And here's sodium chloride solid, and so the heat of formation is minus 411.2. So we just write that in here, minus 411.2 kilojoules. Any questions? Let's do lead 2 nitrate. So the product is Pb NO3 2 solid, because this is what they told us to do. So what are the elements present in that compound? Lead and nitrogen and oxygen, right? Never leave enough space. Well, what do we think the standard state for lead is? Solid. All the metals are going to be solid except for mercury. They're all solids at room temperatures. Mm-hmm. So nitrogen, is that diatomic? Yeah, it is. N2. And what is its state at room temperature? It's a gas. And what about oxygen? Also diatomic, also a gas at room temperature. Sorry, that got so squishy. And then we balance this, and I only want to use coefficients on the reactant side because I want this to be 1. So over here I have 1 lead, so 1 lead works. And how many nitrogens are in 1 unit of this? 2. So if I had 1 mole of N2, I could make 1 mole of this. How many oxygens are in here? 6. And over here I have 2. So if I put a 3 in front of that, then I'll get 6 oxygens. And then to find the standard heat of formation, again, I'm going to look it up in a table. Well, it's not in table 7.5. Here somewhere, there it is. So this is Appendix B, and I've just pulled out the pieces of this that I'm going to need in lecture. So there we see lead, and we can double check that the lead standard state is 0. This table has standard heats of formation, and it also has 2 other columns, and we're not going to learn about those in Chem 1A. Those are for Chem 1B, so you can just ignore the other columns. But then we're going to find lead nitrate down here, and we'll see that its standard heat of formation is minus 451.9. Minus 451.9 kilojoules. Any questions? There probably will be a multiple choice question about which of these equations is the formation reaction for this compound. Yeah. Mm-hmm. Right, it's kilojoules per mole, but the reaction is written so that we have 1 mole. Yeah. When we see delta H, it's usually just written as joules or kilojoules, because delta H next to the reaction is for the molar amounts in the reaction as written. Yeah. Any other questions? Okay, let's see if I'm lost. Okay, got those answers right. There's that table. So this standard heat of formation corresponds to taking the elements and making the compound. If we reverse the reaction and take the compound and break it apart into its elements, we also know what the energy change is. It's just opposite in sign. Okay with that? It's like buying and selling. I sell it to you, you give me the money, I sell it back. Yeah, we get it. So we can calculate the enthalpy change for any reaction by doing sort of a mind experiment. Looking at the reactants and saying, well, let's pretend I'm taking these apart into their elements and their standard states, or basic building blocks. I can look up the heats of formation for those and just change the signs and figure out how much energy change would be required to do that, taking everything apart. And then I can look at my products, there could be more than one, and say, well, now I'm going to take all those building blocks and I'm going to put them together and make these products. And I can also look up the heats of formation for that. So that's what we're trying to do here. So we can take any chemical reaction and write it as a sum of formation reactions. And then we can come up with this general equation here, which may or may not be helpful to you. The standard heat of reaction for a chemical equation is the sum of the heats of formation for all the products, and N here is the coefficient, because if you have 2 moles of sodium chloride, then you're going to have twice the energy change. So you take the heat of formation, you multiply by the coefficient. You add up all the products. And then you subtract the similar sum for all the reactants. It's subtracting because we need to change the sign on those. Instead of making them, we're breaking them. So let's look at this diagram and see if we can visualize what's going on here. So what we're trying to do here is find out the delta H for this reaction. So we have methane reacting with oxygen to form carbon dioxide and water. And we can look at an energy diagram. We've got methane and oxygen are here. And what we're doing in this process with that equation is we're saying, well, I'm going to take this compound apart into its elements in their standard states. So carbon, graphite, and 2 moles of H2. The oxygen is already in its standard state, so I'm just going to leave it alone. And I can look up the energy change for that. This is the decomposition. Here's the formation for that, is minus 74.6. If I take it apart, I get plus 74.6. And then I'm going to take these building blocks and I'm going to make CO2. So I'm going to take the carbon and one of these oxygens and make CO2. And this is the heat of formation for CO2. That's this guy right here, CO2 minus 393. And then I'm going to take the other things that are left, the 2H2 and the remaining O2, and I can make 2 moles of water. And the change in energy here is 2 times the heat of formation. And so what I'm trying to get is the change from here to here, but instead of trying to measure that directly, I can look at these other steps that are known and add them together. So we can do that using Hess's law and these reactions. So I want CH4 to be a reactant, right? So I'm going to write CH4 goes to carbon plus water. And the delta H there, I have to change the sign. And I don't have a lot of space here, so I'm going to leave off the units and the delta H's in all the state symbols. And the other thing I need here, I need O2s. With compounds involved, I need CO2 on the product side. So here's CO2 on the product side. So that would be carbon plus oxygen to make CO2. And I didn't do anything to that one, so that one's still the same, minus 393.5. And the other thing I need over here is water. And so the reaction that had water was H2 plus 1/2 O2 made H2O. And that was minus 241.8. But I need 2 waters, right? So I need to multiply this reaction by 2, multiply by 2, and multiply by 2, right? So then the 2's cancel out. Multiply by 2, and then this gets multiplied by 2. Now when I add these things together, the carbons cancel out, and the hydrogens cancel out. And I get CH4 plus 2O2 to make CO2 plus 2H2O. And then if I add those delta H's, 74.6 plus negative 393.5 plus negative 241.8 times 2. I get minus 802.5. So that's kind of the long, drawn-out way. That reaction, or that equation with the summation signs, what that's doing is saying, well, we understand that we're going to be decomposing any compounds that are reactants and forming any compounds that are products. And so we don't actually have to write out all these chemical equations. We can just look at the heats of formation. So we can say the standard heat of reaction for this is going to be, we're making the products, so we're going to have the heat of formation for CO2, and we're making 2 moles of water, so 2 times the heat of formation for water. Question? The oxygens don't cancel out because I have O2 here and O2 here on the same side, and so they add up to give 2 O2s. They only cancel if they're on opposite sides. Yep. So these are the things I'm making. So I've got their heats of formation because I'm forming them. And then I'm going to look at the things that I'm destroying. And that's the opposite of the heat of formation, so I'm subtracting. So subtracting at the heat of formation for methane plus 2 times the heat of formation for O2. So the heat of reaction is the heat of formation for CO2, negative 393, whoops, 0.5, plus 2 times the heat of formation for water, minus the heat of formation for methane, plus 2 times the heat of formation for oxygen. What's the heat of formation for oxygen? 0. It's an element in its standard state. So that's minus 393.5 plus 2 times minus 241.8 minus negative 74.6. It's exactly the same. It's just a different thought process, and it involves less writing junk down.
But it won't always be possible to do a problem like this, right?
It is always possible.
Totally.
Mm-hmm. Yeah. It's easier, huh? Yeah, it's a heck of a lot easier. Sometimes it can be hard to remember, what am I supposed to do here? Was I supposed to subtract or add, or what's going on? Which one was negative? It helps me to remember that delta means final minus initial. It's always final minus initial. So in this chemical reaction, which part is the final part? The products. So I'm going to take the heats of formation of the products, and I'm going to subtract the heats of formation for the reactants. And I can get delta H that way. Okay, so let's do another example, a real one. The thermite reaction in which powdered aluminum reacts with iron oxide is highly exothermic. Use standard enthalpies of formation to find the heat of reaction, standard heat of reaction for the thermite reaction. So we're just going to use the heats of reaction. We're not going to write out all the equations and add them together. So the standard heat of reaction for this equation, we're going to look at the heats of formation for the products. So we've got Al2O3 and we've got 2 times the heat of formation of iron. But that's an element in its standard state, isn't it? That one's actually 0. And then we're going to subtract the heats of formation for the reactants, 2 times the heat of formation for aluminum, also an element in its standard state, plus the heat of formation for Fe2O3. So it's the heats of formation of the products minus the heats of formation for the reactants. If there's a coefficient, you have to multiply by the coefficient, because if we're making 2 moles of something, the energy change is going to be twice as big. And so then we have to go and look up these values. And I'm going to write them on the board, because my short-term memory is not so great anymore. Fe2O3 minus 824.2. And then we need Al2O3, and that one's minus 1675.7. So I looked up those values, and so I can plug them into the equation. I need the heat of formation of the Al2O3, so that's minus 1675.7, plus 2 times the heat of formation for iron. This is an element in its standard state, so it's 0. 2 times 0 is still 0. So there's my products, minus Heat of formation of aluminum, that's also an element in its standard state, so it's 0. And then we need the heat of formation of iron, which is negative 824.2. So I have negative 1675.7 minus negative 824.2 minus 851.5. And that would be kilojoules. There's going to be negative signs scattered all over the place. You're most likely to get the correct answer is if you just type it into your calculator as you wrote it out. Your calculator knows what to do with subtracting a negative number. And sometimes that messes with our heads and we do it wrong. Any questions? Minus 851.5. There's another one, the chemical hand warmers we talked about at the beginning of the chapter. They produce heat when removed from their airtight plastic wrappers. Here's the reaction. We've got iron reacting with oxygen to form Fe2O3. It says calculate the standard heat of reaction for this and calculate how much heat is produced from a hand warmer containing 15 grams of iron powder. So they're telling us we've got 15 grams of iron. Let's calculate the heat of reaction first. So the heat of reaction, standard heat of reaction, is going to be the heats of reaction of the products. So 2 times the heat of formation for the Fe2O3 minus the heats of formation for the reactants. Well, there's 4 irons and 3 oxygens. And then we have to look these things up. What's nice about these ones at the end here? They're both elements in their standard states. This is 0, 4 times 0, still 0. This one's 0, 3 times 0, also 0. So what we need is 2 times the heat of formation for Fe2O3, which conveniently is a compound that was used in the previous example, and so I still have it written on the board. So 2 times minus 824.2. So negative 1648.4 kilojoules. So we could write that up here. Standard heat of reaction, negative 1648.4 kilojoules. This is the heat of reaction for this chemical equation as written. So this amount of heat for 2 moles of the iron oxide, for 4 moles of the iron, for 3 moles of the oxygen. So that's the first one, calculate delta H. Then calculate how much heat is produced. So this is stoichiometry. Stoichiometry, the starting point is grams to moles to moles to grams. Do we have grams to start with? Well, we've got 15 grams of iron, right? So we've got grams of iron, and we can go to moles of iron, and then what are we trying to find? Heat, kilojoules. So we don't have to do these last 2 steps. We can go from moles of iron directly to kilojoules, because that's what the heat of reaction tells us. So 15.0 grams of iron. I'm going to convert that to moles of iron, and then to kilojoules. And so grams of iron come down here. So the units cancel out. And moles of iron come down here. So the units cancel out. Grams to moles, that's the molar mass of iron. So 1 mole of iron weighs 55.85 grams. And kilojoules and moles of iron comes from the balanced chemical equation and delta H. So their delta H is minus 1648.4. And that's for 4 moles of iron. So I've got 15 divided by 55.85 times negative 1648.4 divided by 4 equals minus 110.68 kilojoules. 3 sig figs minus 111 kilojoules. The question is, how much heat is produced? Should I say minus 111 kilojoules is produced? No. I'm going to say 111 kilojoules is produced. The word produced conveys the direction. I paid $1,000 in taxes. We understand that it was negative for me, right? If we say I paid negative $1,000, then you're wondering, well, does that mean you got a refund? What exactly is that? I won't try to trick you with stuff like this on an exam. I can make no promises about mastering chemistry. So 111. Yep, so there's delta H and.
So can we safely assume that anytime it's asking for what is produced, it will be a positive number?
Right. Actually, anytime it specifies the direction with words, produced, absorbed, emitted, given off, taken in, any words like that that convey which direction, think of it as just using the absolute value of the energy. If it's just saying the heat associated with, or what is Q, or something like that, then we have to put a sign on it because the words are not indicating the direction. Yeah. It's a little bit confusing, I'm sorry.
So these kinds of reactions are all under the assumption that it's like 1 atmosphere of pressure.
Mm-hmm.
Is there a way to correct for the standard state if it was under 2?
Yeah.
Okay.
So it seemed like this was maybe a little too good to be true, right? So yes, we can very simply calculate the heat of reaction for an equation using standard heats of formation. But that's only true under standard states. So this is the amount of energy that would be released provided that we have oxygen at 1 atmosphere. Well, I don't know about you, but in my pocket with the hand warmer, there is not oxygen at 1 atmosphere. It's at 0.21 atmospheres, which is regular air, right? So it's very unusual for us to be doing a chemical reaction that is actually have everything at their standard states. And yes, there are ways to correct this for that. They're not always simple. But it can be done. Good question.